Okay, so last time we did some work, some basic definitions, and then we did review some differentiation rules. There is a nice step here that you have to now note that um, that derivative of a function at a point A is given by defined. This is the definition defined by this either this limit or it is with this one. X goes to A. But then we also have the toolbox of differentiation rules. So what does this toolbox mean? It means that some people have gone through these limits and proved some general facts and gave us as recipes, as rules that we can use when we are trying to differentiate. Okay, so they have done the same definition kind of idea and then done some general cases and they came up with those rules. Now, when someone looks at these two lines, which are basically the same things, but one is more developed tool, a set of tools, says that, okay, if I have this toolbox, why should I use that limit definition? Well, you will use that if specifically we are asking you to uh, to find the derivative using the definition, or specifically if you have piecewise defined function and you're trying to check the differentiability at the separating point. Okay, that's for those ones, there is no other thing. But functions like trigonometric functions or irrational functions or say polynomials, these all differentiations can be done using this differentiation tool. Okay, we can find f prime x just using, or for most of the functions, actually for all the functions that we have, for all functions in this course, using piecewise, using, sorry, differentiation rules. Okay. Now that you have these strong tools, you can kind of go back and give back to the original definition. That's interesting that you can now use differentiation to evaluate some limits. This is the very first step of step of the facts that leads to something called L'Hopital rule. But here today, I'll just use the main definition and so on. Also, you can use, we can find the slope of tangent line to the graph. So these two things are the examples, the few next examples that you will see. Yes, find an equation for the tangent line to the graph of this function. Look at this function. If you want to go with the definition of differentiation, derivative, which gives you the slope, you're in big trouble. Okay. Why do I need the derivative? Because we know that the slope of the line, the tangent line, at a point x equal to a is given by f prime at a. In this case, f is that given function, a is 0. So I go ahead and say that, okay, then if I find the derivative of this function, which is what? Okay, apply the sum rule. The derivative of sine is cosine. Derivative of x to the power 4, in general, power rule says that the derivative of x to the power n is nx to the power 1 less. So it will be 4x to the power 3 minus 3x, use the same rule plus the constant multiple, it will give you 3 plus 2. From this, we know that the slope, I denoted by m, is given by f prime at 0, and that is cosine of 0 plus 4 times 0 cubed minus 3. Oh, I made a mistake in differentiation. Derivative of constant 2 is actually 0, not derivative of constant is 0. So that way we get 1 minus 3, which is negative 2. We found the slope. We also need a point on the line. For the tangent line, the tangent point, the point at which our line is going to be tangent to the graph, the point, the tangent point is the best. So it means that I just need to take the tangent point 0, f at 0. That's the tangent point, a and f at a. F at 0, so sine 0 is 0, 0 to the power 4 is 0, 3 times 0 is 0, plus 2, so that is 0 and 2. And I will use this very general form always for my lines, an equation for a line through point x1 and y1, and with the slope m is given by this formula. So you have the slope, you have a point, so you write y minus the second component of that point, which is y1, equals to slope times x minus the first component. In our case, m is -2. The point is this, so that means that this is x1, this is y1. So the equation is y minus 2 equals to -2x minus 0. And that is y equal to -2x. I take this -2 to the other side. That's an equation for the tangent line to that, to the graph of that function. Any questions, any comments here? Okay. So I will leave the other example. This is example 2, actually. I don't know how I did write 1. This is example 2 of tangent line. So I will leave this one as an example for yourself to do it. So you need to find the derivative, evaluate at x equal to 1. That's the slope. Find the point, the tangent point, which is 1 f at 1, and then use the function, the formula for the tangent line or which I gave in that previous example. Okay. The other topic that we discussed about was that the derivatives can, the differentiation can be used to find some limits. Okay, how? If we can write a limit as what? As limit of a function at x minus a function at a point over x minus x minus a as x goes to a, then we can use differentiation rules and find f prime at a, well, completely different, and know that it is the value of the given limit. So wherever you can write a function, a limit as limit of a function at x minus a function at value over x minus that value as x approaches to that number, we say that, okay, that's the definition for the derivative. I can do derivative from different path. I can do differentiation rules and then evaluate that function. For example, in this case, I see that, okay, there is this x approaching to 0. So I can, most probably, I can take this guy as my a. And then I will try to do the numerator as f at x minus f at a. The denominator must have just x minus 0. But I see that it has x squared minus 2x. So it means that, oh, it's not really a limit of this form. But if I can evaluate that extra piece, see the denominator is x times x minus 2. So I can separate x minus 2 and write it separately. Well, hopefully I will be able to evaluate that. In this case, it's not difficult. The other part, which is minus cosine x e to the power x plus 1 over x as x goes to 0. Now, well, the first part is just quotient law, yes? So this just quotient law gives me what I'm looking for, which is 1 over 0 minus 2. For the second one, this is f prime of some f. I will tell you what is that f at 0. Okay. For what? So for f, so I have to define f such that then this guy here is f at x minus f at 0. Okay. So I can, well, there are more than one way to do this. I can assume that the function is minus cosine x e to the power x. Or, for example, I can assume that the function is minus cosine x e to the power x plus 1. Either way will work. Well, I will do the first one myself, and I'll ask you to do that one yourself. But the first one, if we go with that, f at 0, then will be minus cosine of 0 e to the power 0, which is negative. And then we see that f at x minus f at 0 is nothing but minus cosine x e to the power x minus -1, which is minus cosine x e to the power x plus 1. Yeah. And over x minus 0 over x minus 0, this is exactly f x minus f at 0 over x minus 0, which is what we have there. So that is our function. We found it. We confirmed that we have the limit which defines the derivative of that function. Now I can go ahead and find the derivative of this. Derivative here, I need to use the product rule, which is derivative of first one times second one plus the first one. Okay, maybe I just write it the way it is. The first one itself times the derivative of the second. Derivative of cosine x. Can anyone tell me what is derivative of cosine x?
Minus sine x.
Minus sine x, and there is a negative sign there, so it will be sine x e to the power x minus derivative of e to the power x is
e to the power x.
E to the power x. Thank you. And now that we know what is f prime, I can just evaluate it at 0. That's sine of 0 e to the power 0 minus cosine of 0 e to the power 0, which is 0 times 1 minus 1 times 1, and that is negative. So you see, we saw the pattern that this limit is the derivative of this function here at 0. I use the differentiation rule, and we found that f prime at 0 is 1. But since I already have that, I know that now I have the value of the limit. And that's how I use the definition of, I use the differentiation rules to evaluate some nice limits. Any questions, any comments there? Okay. Yeah, sometimes this will, but by the way, if you start this limit from the beginning, you notice that this is at the very beginning, you know that this is 0 over 0. So if you start from the basic idea 0 over 0, that could be the source of where you start thinking of how should I deal with this thing. One way is that I turn this or part of this limit as a limit that defines the derivative of function at a point. Okay, another example. Yes, okay, so this is also an interesting example. This is well, there are more than one way to solve this. I want to use the fact that limit of sine of x over x as x goes to 0. We showed this by squeeze theorem that this guy is equal to 1. And indeed, in general, if instead of x, you have any other expression, which has the same sine of box over box as box goes to 0, the limit still will be 0. And it's good to watch that video that we have on week 5. this limit comes up when you're trying to find the derivative of sine x at 0. And actually, that's enough. If you know the derivative of sine x at 0, you will be able to find the derivative of every other trig function just by knowing this limit, which is derivative of sine at 0. I think if you follow the videos or notes, you will see that how this works. I want to use this fact and try to solve that limit. So I see that here I have sine of x squared minus 5x plus 6 over x squared minus 2x minus 3 as x goes to 3. As x goes to 3, limit of the denominator is what? This is polynomial, it's continuous. So limit is the same as evaluating. So 3 squared minus 2 times 3 minus 3, this is 0. 9 minus 6 minus 3. And whatever I have inside sine, this is also, oh, that goes to 3. This is 3 squared minus 5 times 3 negative 15 plus 6, 9 minus 15 plus 6, that's also 0. It's not, it is 0 over 0 case, but it's not just a polynomial over polynomial. I cannot factor and just take out the vanishing factor because there is a sign applied on that polynomial. Instead of that, I try to put my function or my limit in this format here. I say that, okay, see, there is a box here. As x goes to 3, the box goes to 0. So how about I try to generate the box in the denominator. So that box in the numerator is this. Well, I will put that box in the denominator. Sorry, the same thing in the denominator. But previously I had this denominator, so I should not forget that. Since I divided the expression by that box, I have to also multiply it by the same. I'm doing all these things because I want to generate this pattern, sine of something over that thing as that thing goes to 0. I'm almost there. If I can compute the limits of each piece separately, then I am good there because yeah, this is the box. This is the box, sine of box over box. As I have to make sure that box goes to 0. Note that box goes to 0 as x goes to 3. This is exactly this calculation that I showed you here. So that means that I'm dealing with the first one is sine of something over that something as that something goes to 0. The second one, however, is well, if I compute that, I notice that I get 0 over 0. Again, the same calculations that we did here. 0 over 0, I have to factor it and cancel the vanishing factor. Remember, vanishing factor in this case is x minus 3. So I have x minus 3, x minus 2, x minus 3, x plus 1. That's just the factoring that works there. And I can cancel the vanishing factors. I can go ahead and write the limit after canceling. And this is 3 minus 2, 3 plus 1. This is basically quotient law, and that is 1 over 4. The second limit is 1 over 4 after doing some work. The first limit, well, I know based on the fact given above, this is just 1. So using the product law, I can continue and write that this is 1 times 1 over 4, and that is the whole limit is 1 over 4. And well, I could have seen this as sine of box minus sine of 0 over box minus 0 limit as box goes to 0, which is the same thing as the derivative of the sine as x is equal to 0, which is cosine of 0. There's a loop there, but now that you have all those facts ready in hand, you can go ahead and use one or the other one, doesn't matter. But this is basically what you can use also. How you can use derivative to find a limit of some limits. Well, this tool will be developed a little bit more, and we will be able to do way more general cases using what's called L'Hopital rule. Below, yes, please.
Sorry, just to verify, you got rid of the sign when you were using that rule, and then multiplied like I guess one value and by the other one that like you know how you separated.
Sorry, are you talking about this step? Wait, this step.
The one right below that. Or
Oh,
yeah,
this is just product. This multiplied to that. The limit, I can find limit of the first part times limit of the second part, and then multiply the limits.
okay, because I saw that the I guess that the sign, or you got rid of the sign and you did that by
No, I didn't got rid of the sign. That's not what I did. I just separated. This is limit of f x times gx as x goes to something is the same thing as you find the limit of the first one and find the limit of the second one and then multiply them.
Okay.
Yeah. Yes, Adam. Yes, please.
Hello, Professor. I was just wondering, isn't it possible to do this question the same as the one we just did before that?
Yeah, yes, the last comment I gave was this, yes.
Oh, okay.
This is kind of pointing the same direction.
Oh, okay. Thank you.
Okay, I have one more example for you to do this one yourself, and while you now probably see what is the point, turn it to f prime of something at somewhere. Yeah, so this is f prime of a function, I can say at 0. And then you do that part. You can do it yourself. Just go ahead and try to compute that one. So you can take a screenshot of this, and you can actually use the fact that also alternatively you can use the fact that sine of e to the power x minus 1 over e to the power x minus 1 as e to the as x goes to 0 is 1. Definitely, there is more than one way to do this problem, but try both of them. Try to see if you challenge yourself in using different tools that are available in this course. Sometimes for some problems, one tool is available and the other one is not available. So if you're trying to master the topics, if you see an alternative way, try to do that alternative way as well, so that you see different aspects of the same problem. Yes. So the last topic for week 5 is chain rule. So remember that we covered product rule, sum rule, difference rule, quotient rule, and constant model. So these are all the different ways that we can generate a new function using the two old functions. These were called combinations. So the rules that we covered so far tells us how to differentiate combinations of functions. Now, there's another way to generate a new function. It's called composition. Chain rule is nothing but how to differentiate compositions or composition of two functions. Well, is the composition of two differentiable functions differentiable first? And then, so that is the chain rule. It's written in terms of the theorem. I'll write a little bit details of this, saying that let G be a differentiable function at A, and F be a differentiable function at F at A. Sorry, at G at A. So G is differentiable at A, F is differentiable at GA. Then the composition of these two functions, FOG at X, is differentiable at A, and the derivative is given this way. You differentiate the inner function. You see, this I can write it as this, yes. And then I first differentiate the inner function, then multiply it, differentiate the outer function, but you have to plug in or evaluate that derivative, not at x, but at gx. Yes, this has different forms to write down, but this is basically the one that kind of gives you the feeling of the chain rule. Apply chain rule twice. And it will give you this thing that is more that shows more where this name comes from. So you pick one, like this chain is getting one by one from inside toward outside. So derivative of the very inner one times derivative of the second inner one, then the derivative of the very outer one. But each one will be evaluated on different values. The derivative of the very inner one will be evaluated at x. The derivative of the second inner one will be evaluated at the value of the inner one. and the derivative of the outer one will be evaluated at all the other inner ones at that point. So you just take out one by one, kind of like chain. That's where the chain rule, the name chain rule comes from. Is there any questions, any comments before I go and do some work there, some examples? Are you guys feeling okay there? I see that people are leaving the room. Oh, how come? You don't like chain rule at all? Let's do some examples of chain rule. I like these type of questions because that kind of gives you tells you how you use that these rules. Yeah, how you use these rules, and then don't get yeah, these are just checking different rules, not necessarily the chain. For example, the first one, h prime at x, this is quotient rule, yes. So here I need, I will make it a little bit larger. So I will need the derivative of numerator. The derivative of numerator, gx plus e. The derivative of gx is g prime x. Derivative of e, can anyone tell me what is derivative of e?
0.
0. Don't confuse e by e to the power x. E to the power x is a function, sends x to e to the power x. E itself is just constant, like 1, 2, 10, negative pi, pi, e. All these guys are constant. Derivative of constant function is 0. Numerator, derivative of numerator times denominator minus the numerator itself times the derivative of the denominator. Here will be f prime x plus 2x. And then the denominator squared. Okay, I will go ahead and then evaluate x at 2 or x at 1, whatever was that point. I'll do it at x at 1, doesn't matter. Well, x at 2. It says evaluated at 2. So at 2, this is g prime of 2. What is g prime at 2? It is 2 plus 0. F at 2, so f at 2 is 4, and plus 2 squared minus g itself at 2 is 3, and f prime at 2 is 0, and this is 2 times over. F at 2, I believe this is the one, is 4 plus x, well, again, 2 squared to the power. I have all the values. I can go ahead and compute that one. I will leave the rest for you just to complete. This is a straightforward calculation. And this had nothing to do with the chain rule. The second example is for the chain rule. So here, derivative of f of g is g prime x f prime at gx. When you plug in x equal to 2, this is g prime at 2 is 2 times f prime at g at 2. But g at 2 is 3. Now, f prime at 3, this is f prime at 3 is 1. So 2 times 1. So we have that one ready. I will leave this one for you to complete. This is not only chain rule, but also the sum rule and product rule also is there. I'll do this one. So this is nice. So h prime at x is, so I see that, okay, f is composed with this. Now I have to find the derivative of the inner one times the derivative of outer one, which is f prime evaluated at inner one itself. Oh, okay. The second term, I cannot do anything because I don't know what is the general formula for f prime. I just know the values of f prime at some point. But for the first one, well, first of all, this is product, a constant multiple rule. Sine of pi over x itself is composition of two functions. It's sine composed with pi over x. Then it means that I have to find the derivative of inner one times the derivative of sine, outer one is sine, the derivative is cosine, evaluated at inner. Pi is constant. Again, this will be 1 over x prime, cosine of pi over x. Derivative of 1 over x, you should be able to do that just by applying the product, the power rule, n x to the power 1 less. This is -1 times x to the power -2, which is -1 over x squared. So this is now pi times -1 over x squared times cosine of pi over x. And I found that one now. I can plug it in here. Just 3 pi minus over x squared sine of cosine of pi over x f prime of 3 sine of pi over 2. When you set x equal to 2, this is where all the works comes from. So this will be -3 pi over 4 cosine of pi over 2. I'm plugging in x equal to 2, and this will be f prime evaluated at 3 times sine of pi over 2. Sine of pi over 2 is 1. So, but cosine of pi over 2 is 0. Okay, so that means that we have 0 f prime at 3. Well, f prime at 3, you can find it from the table, but this value, the whole thing will be equal to 0. Any questions, any comments from me?
Sarah, could you zoom in a bit? Sorry, I didn't.
Zoom in, you mean?
Yes.
On this example?
Yeah.
Sure.
Yeah, that's fine.
Oh, you wanted to take a screenshot?
Yeah.
Yeah, okay.
Thank you.
You know that I post these ones, the PDF of
Yes.
these. Okay, good. Okay. Any other questions? Any other comments? Well, when you learn the chain rule, then the table of differentiation table kind of changes now. Meaning that before, for example, we had power rule. This was dx of x to the power n. This is n x to the power n minus 1. If you apply chain rule here, chain rule means that instead of x to the power n, you have a function to the power n. In that case, you will have nu to the power 1 less. That's still there, but chain rule says that you have to multiply it by the derivative of inner one, which is u prime. Or for example, when you have e to the power x, the derivative is e to the power x. If you apply chain rule, it means that we are composing e to the power x by a function u, and the derivative is going to be e to the power u, the derivative of this guy evaluated at u, but you have to multiply the derivative of inner one to that guy, u prime e to the power u. Or derivative of sine x is cosine x, and then you have derivative of sine of a function is u prime cosine of u. And you have to be able to write everything in both cases. How does that going to help us? For example, this guy, now it is u to the power n. Then the derivative is going to be u prime times n u to the power 9. And that is 10 times 4x cubed minus 12x squared times x4 minus 4x cubed plus 3 to the power 9. This guy, you see that is this e to the power x plus 4 sine of x to the power 1/3. Now the derivative is going to be 1/3 u prime times u to the power 1 less. And well, that is 1/3 e to the power x plus 4 cosine x times e to the power x plus 4 sine x to the power negative 2/3. You can do this one yourself. That's just power rule plus chain rule again. I will do one of these guys as well. So this is derivative of cosine of some function. I know that the derivative will be the derivative of that function times derivative of cosine, which is negative sine, evaluated at this. And this is 2x minus cosine x times sine of x squared minus sine of. And I will leave the very last one again for yourself to complete that. That's just chain rule. You need to apply chain rule twice and get that example done. That's it. That's what I had for today. Let me just pause the recording.